Okay, let's begin the last talk session of today's seminar by the Dr. Shinji Sumimoto. Dr. Shinji Sumimoto is now the project professor at University of Tokyo's Supercomputing Research Division from the 2022. And before that, as you know, Sumimoto-san has been working in the Fujitsu, and he developed a PMV2 for the SQL WCP project, and also many other cluster computing, like RIKEN, the Super Combined Cluster, and the University of Tsukuba's our PAC-CS cluster. We worked together there. And after the Tech Computer project, and he developed the interconnect and system software, and also that for the Fugaku, he led the ARM HPC open source software activities. And now there, excuse me, I'm confused at which part should be shortened. Anyway, so he then worked a lot of system software and high performance communications, covering the process architecture, communication hardware, Linux kernel, and the MPI communication libraries. And he's now involved into the H3 Open BDEC project in the University of Tokyo, and also JCAHPC quantum project with the University of Tokyo and the RIKEN, and developing the H3 Open Sys WaitIO, and maybe the talk is related to this project. And sorry, and also it's in the router variant. Okay, please welcome Sumimoto-san.
Thank you very much for the country introduction. My name is Shinji Sumimoto from University of Tokyo. So today I'm going to talk about a little different scope of the communication library. It's a high-performance center-wide heterogeneous computing with WaitIO. It's not all the MPI config, but it's all of the combined MPI program into the another space. That's my talk. So here's my overview of my talk, and I talk about some WaitIO BDEC on our system and on the HC Open BDEC, and then go to the WaitIO overview and its application, and then go to talk about some of the current WaitIO development at the JCAHPC quantum project. So let's start. So we are now operating some WaitIO BDEC for over 4 years since 2021. It's aims for developing simulation plus data plus learning. And WaitIO BDEC one is the world's first real heterogeneous computer system. How do you mean? WaitIO BDEC two kinds of system. One is Aquarius. It's a Intel CPU and NVIDIA 8A100. And also Intel MPI and Intel CPU and the NVIDIA some developing GPU stuff. And also in the commercial version of Fugaku, it's a Fujitsu development, and on the processor HPX and the Fujitsu MPI, to the interconnect, and some of Fujitsu MPI. And so we need such kind of combined system. However, single MPI can't run in Odyssey and Oculus. This is completely different MPI and processor. So we did some WaitIO communication library. So that's because simulation Odyssey and Oculus is connected by 2 terabyte InfiniBand and also 2 types of shared file system. And so we developed some HC WaitIO socket. It's a library for interprocess communication through Infinite EDR and MPI-like manner. And also my colleague developed H3 Open UTMB. That's a high-level functional coupler with multiplexer and button general way. So on top of the two kind of software, we also developed a coupling job scheduler. This is this kind of two systems operated by 2 job scheduling, TCSO and TCSI. And using some coupling job scheduler, user submit 2 jobs for each system, but with special resources. At the time, this coupling job scheduler looks into availability of 2 kind of nodes, and 2 resources are also available. 2 jobs start to run at the same time. And I talk some with the Open BDEC. It's the innovative platform software for integration, simulation plus data plus learning. And there are 3 innovations. One is a principle of numerical analysis and adaptive precision. That's an automatic tuning and accuracy verification. The other thing is highly data-driven approach using machine learning. And the third topic is software utilities for heterogeneous environment such as visual background. I talk some third topics. And actually, I know basics in the it's very easy. WaitIO into some this figure shows some took a 3 MPI job in the different sum. However, using WaitIO, user can choose any of the process, selection or some process, and creating a WaitIO group, then go to some creating on top some maybe a WaitIO group is the same as a communicator on the MPI, and also some MPI I send, I see, receive, and write. That's only. It's very easy way. And also, it's because the words of WaitIO MPI conversion library, because WaitIO doesn't have MPI data types. So WaitIO MPI conversion library is like I send, I receive, reduce, because it's not for churn, but it's some works. And for example, some of P3 application conversion input sample. It's very easy. This is a P3 3D hit propagation program, and also such kind of thing. And this is written by Fortran, but to transfer some WaitIO, use some header and also prefix WaitIO underscores is mainly. For example, this is I send, the WaitIO I send, and also double precision in the WaitIO prefix. No, same manner. Also some audio is also same. And here's the performance in the WaitIO circuit. Actually, this is running on Odyssey. It's not fast because some ASIC socket and commission is not so good. And also here's some using some WaitIO circuit. It's around some 200 megabytes per second. However, this is using WaitIO file. It's a shared file system using. It is up to the 1 gigabyte per second. It's not so good, but it can be connected. So what is the application is WaitIO and UTLP application? One is some real-time 3D access simulation. It's a combination of the real-time data processing and simulation. And in this case, in the accuracy in the data filtering, visualization, and also Odyssey in the simulation and the data simulation. And actually, Japan has so many scales. And there are sensor networks, and we can be observed the data from the Science 6. It's JX on the JX net. So we should be accuracy get observed data here and filter some data and send it Odyssey to the some simulated data. And in the Odyssey, run the open time sequence and data simulation and go back to the visualization. On top of this is accuracy side only send and the Odyssey side receive. That's only. And also the other topics WaitIO and UTMP application. It's a simulation and machine learning, Python coupling. In this case, it's a NICAM. It's a very problem is some high resolution, maybe cloud reading. So much needs computer resource. However, in a climate simulation, it is very tough to simulation to. So in this case, it's learning from the high resolution to a low resolution processing to machine learning. And so use some machine learning and using some small resolution parameter, then go to come back to the high resolution couple. To really that thing. Actually, here is some output data. Here's the input, and here is simulation data, and this is prediction of the machine learning. It's almost similar, but a little similar, but we need to improve that thing. And here's some applications. Well, we need NICAM and machine learning. It's a continuous this communication. Here's the result of the Odyssey like solving a homogeneous manner. It is a Nikon with run on Odyssey and machine learning part also Odyssey. And here's the fiber. This one. And this one is some Nikon run on Aquarius and Odyssey and machine learning part in Aquarius. So CPU plus GPU is 35 faster than the CPU plus GPU. That's the way it's the WaitIO way. And also WaitIO is aim to provide a coupling MPI job. In that case, weekly job coupling is maybe mainly use files. Maybe one position file up to the file, then go to another window file, read the file. In that case, that kind of file is removed and changed to the WaitIO manner. That's it. And also, this heterogeneous coupling processing also possible. Here's some one big issue, but we using a WaitIO divided it into the CPU part and GPU part. It can be run on the simulation. And we are now going some JCPM project in the heterogeneous computing. And University of Tokyo and JC and some other foreign maybe laboratories. Because of University of Tokyo, with the and some Uric computing, JC, led by Estella, they did some modular supercomputing. It's a very, we are going some same way. We are collaborating on congenial application. So here's a workshop, and we present heterogeneous computing. At the workshop last year, we took some several, going to several applications, TSMP and case and brain animation and CMO. But in this presentation, TSMC and JC, we are brain animation simulations. So I like some topics from the paper. And the final goal is the application portability in a comparison. And currently, JC has some real application on a deep system. So, in this project, we implemented the application, maybe mainly TSPC and Maya, going to the deep one, which is HTTP OpenBDEC, and compare the performance of the deep and with the BDEC. And maybe you know about the deep system is a prototype system modular supercomputing architecture. They own some computing cluster module, it's a CPU module, and also ESMP is a CPU and GPU module. And also there's a data assimilation and the storage module. And we go to some disk. And here's the topics. Cluster module is maybe 50 node and infinite EDR, Xeon, to socket. However, booster, it's a GPU part is one socket of Xeon and one socket of V100. So I took some of Maya version. Maya is developed by Aachen University. It's some of full dynamic simulation, and it will compose some of partial solver, LB, lattice Boltzmann, design, some real, and also some coupler. So Maya is a combination of some solver and coupler, so and their applications. So we think of some how WaitIO should be implemented this kind of application. One type is it is very easy thing. Maybe for example, the lattice Boltzmann and post data the target, and this lattice Boltzmann is maybe relative MPI and also post data MPI, and WaitIO is coupling. This is maybe right away. And the other thing, type B is many of some written by WaitIO, and the same application of different architecture at the same time. And I took some result, and which are type application. It's running on a deep system and Odyssey. In that case, this is the Odyssey part, and also compared to physics MPI. And this is a deep part, and with the comparative Intel MPI. This is maybe which Odyssey is not so good performance, but scalability good, and maybe increase the processor number of processor is almost same. And here's a very interesting topics. These are type B topics. we run on the some part of the ARM and just a part of the CPU in the Intel. It's because of limited number of node of Acreus, it's only a combination of 122 Odyssey the 64 and Acreus 64 process, and also Odyssey the 448 process and Acreus 468. But it can be same result and scalable. It's a very it's a fast time. So I leave to focus on next wait of development is a JCAHPC quantum project. So actually, JCAHPC quantum project have a system quantum simulator plus supercomputer, and this is 2 years ago. So actually, yesterday there are ceremony that because IBM quantum computer in the leading site in the opening ceremony. Here is some IBM quantum machine, and here's a mock-up of the quantum phone. So in this project, we have the JCAHPC and software project leader, and we Invest Tokyo and Osaka we joined to the project. At the project, we Invest Tokyo has planned some system for QCHP hybrid environment. On that basis, we plan to develop a QH schedule, a job schedule that can be simulated. Because in Japan, SciNet is very high, 400 gigabyte BPS network, and there is the QC and HPC on several sites. We combined this scheduling to the multiple job onto the among the jobs. So also, we developed some scheduler and also a commission software. It's coupling to FCH implementation, the integrated connection, data transfer. So it's the WaitIO development, WaitIO router development. For the WaitIO development, it's a center-wide communication. In that case, it's the same binary, no different. But in the center, hyperfast communication using RDMA and zero copy routing. So we develop WaitIO verbs and WaitIO TOF. And also WaitIO router for zero copying is now developing. I'll talk about it later. And also among centers, so converting a single stream to multiple stream. Because SciNet is some wide area network, high latency. In that case, single stream is not performance effective. So we divide the single stream to multiple stream, and also for security with encryption and scrambled buckets. Here's a WaitIO software architecture. It's a WaitIO API and RDM part and software and file component and router. And here's some performance WaitIO verbs. Here's Acreus. In that case, one way latency is 1.3 microsecond. However, WaitIO socket 12 microseconds, maybe 1/10 is faster. And bandwidth is for socket 4.2 gigabyte per second. However, Acreus has a 4 HDR infinite. In that case, if you have 4 multiple processes in a node, WaitIO is gathering to some combined the bandwidth. So one stream 24 gigabyte per second, 2 stream 49 gigabyte per second, and the 4th stream which 96 gigabyte per second. So we come to high bandwidth among the applications, MP applications. And here's the market. Also, here's a H100 for NVIDIA 400. In that case, almost same in the scale of bandwidth. One stream in the 48 gigabyte per second, and also 4th stream 191 gigabyte per second for among applications. Also, I talk about some WaitIO TOF in the Odyssey. So actually, last part, WaitIO socket in the Odyssey is not good. However, using a WaitIO TOF, it's around some 3.4 microseconds. And WaitIO socket 36 microseconds, so 1/10 of latency. And bandwidth is also one socket bandwidth 222 gigabyte per second, but using a WaitIO TOF, the 6.4 gigabyte per second. So of course, WaitIO is run on Miyabi. it's some, we discussed CPU, GPU based upon acceleration part. Also, a CPU group is a CPU only introduce Max into Sapphire Rabbit. It's connected by NT1 200. So performance almost same. Some Miyabishi, and some Miyabishi, some GPU and NVIDIA. Here is some Miyabishi and Miyabishi. It's a heterogeneous networking. This is weighted barbs in the Miyabishi is 1.6 microsecond, and socket is 4.9 microsecond. And Miyabishi and is almost same. And also bandwidth is almost same. And weighted socket in the 6 gigabyte per second. However, weighted barbs is 24.8 gigabyte per second. It's almost G and G almost same. So we realize some high bandwidth communication into the multiple internet. So I like to some RDM communication issues, so memory ID relation. Maybe GK is very well known. It's infinite bounded memory relation. So lazy and so slow. Because we measure such a resolution is around 27 microsecond. This is a real application. And the release also of 18.6 megabyte. So we need such a memory relation cache. So here's the result of P3 application. And here's solver in a flow. It's just a Nagoya University talk. It's a solver in Intel MPI, and this is a socket in WaitIO and also barbs. And this is weighted socket is a bar is with the barbs is faster than the socket. And for the OSA case, which is MPI in the weighted socket and weighted TOF, weighted is relative. However, if this relation cache is not existing, so here's the result. And actually, weighted socket is faster than weighted barbs. And at the time, we added some adapting manual relation after MROC. This is an allocation of the memory and introducing a weighted register memory and register memory. In that case, I leave it to fire. So we need to care about some memory registration. So let's talk about weighted router development on the weighted bit 1. This is maybe main topic of this presentation. Because what I say is some top integrator. So when we dispatch 2 jobs in the Odyssey, socket communication in the among the 2 jobs can be possible, but direct communication in the TOF is not permitted because avoiding interference of jobs. So we some kind of developing weighted router. So weighted router support this kind of directly connected is not good, but using a GIO and using an infant and goes, it's possible. So we need to have development. So here is some router and performance. Here's a weighted TOF latency. It's around 3.5 microsecond. And with a socket, uses 36 microsecond. And also with a router, it's 12 microsecond because 1 TOF, 1 infinity band, and 1 TOF. So maybe 3 times slower, which doesn't make sense. And also bandwidth is much higher. With using a socket, it's almost 221 megabytes per second, but using a with a router 6.2 gigabytes per second. And more detail will be presented in the SOAP in Japanese, but in June. The other thing is WaitIO for Pi development. Because we developed WaitIO Pi to interface with WaitIO. Because communication, MPI communication, and Python program directly. Because many of QCs use Python-based tools. So we developed and support the thing. So application can be used the same API with C and Fortran program in Python. And also, this can be set ranks and attend to the convention. What the case is one is C language and C Fortran language, and two kind of Python program can be connected. Actually, it's very easy to the some ranking goals. Yeah, here's a code is some Python, and run is here, and this is a Python coupling. It's very easy. Yeah, here's the result of the thing. It's a ping pong program, and also C language once here, and also some program Python C coupling is also run. So here's some programming interface. It's a class object, waiter group, and waiter ranks, and waiter size, request, because of some Python manner. And the communication is very limited, but only some waiter send. But using some waiter part, user can connect by a Fortran API, and also machine learning and GPU, and also connect by a Python QC2. And here's anything posting the waiter. It's my end of talk. Thank you very much, John. So we need some tech questions.
Some comment or even from the online audiences. Anything? Oh yeah, DJ, please.
Can this software work on coupling any machines, or how portable it is?
Oh, just only a copy of the waiter.so. That's only.
Okay.
If we have some account on the machine,
Okay.
and the library, it will work. Not because doesn't any, for example, that's because socket, that's
Yes.
okay. If the machine does not support for the direct connection node, we can use, maybe you can use the shared file system. In that case, shared file system, the combination also possible. And the other thing is that if we implement, it's a bugs, it's like some GPM. And also, user can use the waiter anything.
Okay.
If you have account, you can combine.
I think that the DK's question is how general or portable
Yeah.
any system.
How portable?
Yeah.
How much kind of different system tested?
Okay.
Right?
Yeah. I mean, so along that line.
Yeah. This is some flow. It's some FX1000 and some GPU machine. It's connected by shared version because that doesn't permit socket connection the other time. And also with BZ1 and MIRB and also a deep system. It's currently. And also a Kyoto University system I tested.
Do all these systems need to be in the same center, or can they be geographically distributed?
Currently, we have plans. Maybe this September, we plan some MIRB to Fugak connected. We plan, so that's our mission, and also connected by QCs.
Question?
It's only a socket, so
Yes.
if you have IP reachable, you can use.
No question from the online audiences. Okay, so that time is almost limited, and
Yeah.
so
Go here.
it's good to conclude the session. Okay, thank you.
Thank you very much.